Well, hello, and we are back for Sedimentary Rocks. You are looking at Zion National Park. This is from above my mantle at my house, and the sandstone rocks, or it looks like hoodoos, which you'll learn about later in the semester, these things. Those come from a friend of mine who make these out of rocks. They actually use pneumatic tools and carve just a plank of rock and turn it into that and put it in an oven and make the oxides come out. Hematite, you learned about that in minerals. So we're going to get right into it and talk about what you need to know. If you've not watched the lecture video and read your book, absolutely need to do that, just like you did for the others. And let's start by talking about how easy sedimentary rocks can be to identify. There's just a methodology like there was for igneous rocks and looking at if the crystals were interlocking or not, and versus looking at color. There's a similar system for doing sedimentary rocks. So there are two types of real major groups, and there's what's called clastic or detrital, and that's the same thing. And those are made up of fragments of rocks that have broken down. So that could be any rock type. It could be even minerals, sedimentary rocks that have broken down, weathered down, igneous, metamorphic, you name it. So it can be anything that gets broken up and gets deposited into a rock like this. And you go, I can see that, you look at this diagram up here and how it gets compressed and compacted together and cemented together. You can see that, which is be similar to this rock. This is no different, except in one way. The sizes of the clast, which these things are classed, these individual particles are classed, are much, much smaller. So what this does for geologists is it gives us clues. And the clues tell us what kind of depositional environments that these rocks were formed in. So that's why you needed to learn about depositional environments before this lecture or this lab in section 6. So let's move on and say that there's a second major group of rocks, and there's really several different kinds. There are just chemical sedimentary rocks, and then there's biochemical, but we're going to kind of lump them together. This is an introductory course, but essentially, most of your chemical sedimentary rocks come from several processes. One is some kind of aqueous reaction, meaning in water, where you get a sediment that's actually precipitated out that makes a solid. Oftentimes, chemical sedimentary rocks contain little microscopic organisms like you see here. And I mean, when they're tiny, they usually requires a scanning electron microscope to see them, not just a regular microscope. These are little living creatures, and so as they die, they create layers, and these things make the sediments that can make a rock like this, which is limestone. So when you're thinking about like oil and gas, usually those come from little tiny things. I'm not saying they can't come from bigger animals like dead dinosaurs, but a majority of those reservoirs come from this kind of stuff right here. So when you're thinking about the difference between detrital/clastic versus chemical and biochemical rocks, you need to be thinking about the source of material. So it's not that a piece of limestone couldn't have a clast in it or even quite a few clasts in it. That is certainly the case. What the difference is a majority of it made up that with chemical or biochemical processes, like 50% or more. If the answer is yes to that, then it falls in that category. So clastic rocks, there's just a few groups, and they're pretty easy to classify, and really, quite frankly, so are chemical and biochemical. All right, samples 1 through 10 in your lab are in your packet or your little envelope, plastic envelope, that looks like this for sedimentary, section 7 lab, sedimentary rocks bag. And I need you to get your lab space ready. Before you ever do any lab, I'm asking you to do that. I'm asking you to get your testing equipment out. I'm asking that you would take a moment to go ahead and test each sample using your items that you have, meaning your street plate, your hardness, tools, the magnet, and of course, if you've got the acid, that is really great in sedimentary rocks because many of them may have calcite, so you'll get a reaction. And each time that we work with a sample, get it out, let's test it, let's analyze it, and let's kind of run it against the course or the frame of, all right, do you think the sediments were put together by breaking up of other rocks predominantly, or do you think they came from the development of dead microscopic animals or some kind of precipitation chemical event that created a solid that made this rock? And the key with detrital/clastic rocks are understanding that you can have the really tiny, tiny, tiny clast that get weathered over time more and more and more. And so you get a lot of these tiny little clasts, which can be mistaken for chemical sedimentary rocks. Let me take one more moment. Just because something reacts with acid does not trump it as being automatically chemical. It just means it has calcite in it. So that's an important thing to keep in mind in this lab. So now that you've gotten out all of your samples, I'm going to ask that you secure your room because you're going to need to touch and feel these samples against each other, meaning when I ask you to touch sample 1 versus sample 2. So I know it kind of goes a little bit against what I told you to take them out all at once, but spread them out so you don't knock them off. These don't look so similar. So if you got it, take a picture before you do it so you can get them back in order. That's always a smart thing. But in sedimentary rocks, feeling is a really big part of it. And that's one reason I want you to do this. So I'm going to take a few moments to go over the various different characteristics of each of these rocks that you'll see on these slides. And then that will help you make determinations as you touch them. So if something's detrital or clastic, as we mentioned earlier, it's made of predominantly of fragments from other rocks and minerals and sometimes even organic debris. But the key is the size of clast. You're like, well, I don't know how to figure that out. Part of it is experience. I get that question a lot is, well, I can't really tell if it's shale or siltstone or sandstone. Well, seeing and touching various different rocks will help you with that skill set. This is just a preliminary start to your experience with that. But here's the deal. When you're looking at clastic and sedimentary rocks, the easiest ones of the clastic detritals is conglomerate and breccia, because the 50% rule of this morphology of the sediment applies. So if it's predominantly rounded sediments, meaning clast, then it's conglomerate, if they're big enough to see without a hand lens, without a microscope. And that doesn't mean every single one will be big enough for you to see, but it's an average. If you get to predominantly having big enough clast you can see that are angular, then you've got a breccia. So that's that kind of marker of 50%. That's just a good rule of thumb. When you start getting into sandstone, it feels sandy, but there's a degree of sandy, right? If you even buy sandpaper, you know that there's different types of sandpaper, meaning from smaller grains size to a larger grain, depending on what you're trying to buff or sand down. Same is true with the sandstone rocks. So they go from 0.0625 millimeter diameter of clast size up to 2 millimeters. Now I realize there's a 2 millimeter max for sandstone and a 2 millimeter minimum for conglomerate and breccia. But remember, it's an average. So most sandstone has a sandy feel, but keep in mind sandstones with clast sizes that are closer to the 0 or 0.0625 are not going to be feeling as sandy as stuff that's almost 2 millimeters. So you have to use some judgment. So same thing is true with siltstone. So let me talk about shale first and then come back to siltstone. Shale is so tiny that, meaning the clast, they're usually somewhat microscopic in size. So to use a hand lens or a microscope, it's possible you could see some grains, but likely they're so tiny, it's just a wash. You can't see it. So it's very smooth, and it takes a bunch of these clasts to make even a small amount of rock material. When you feel siltstone, it's somewhere between a shale and a sandstone. So it has some grit to it, but it's softer and it's not nearly as rough as what you would feel with sandstone. All right, let's move to the biochemical rocks. So as we get into the chemical sedimentary rocks, I want to take a moment to explain them and to say that this is probably the more challenging of the rocks to identify, because you're like, well, I'm not sure. The easiest one will be chert and flint, because you've probably seen it as arrowheads. So chert and flint is actually reprecipitated types of limestone typically, but the animals that reprecipitate them, usually in some type of a marine or aqueous environment, is what dictates whether it's chert or flint. This is well beyond the scope of this class, but you need that information and knowledge so you are using the right terminology. Most of what we have in the United States is chert. I realize there's a city called Flint. Just know that people use those terms interchangeably, and so if there's an area that has a lot of chert, then they may consider it flint. I'm not saying there's not flint in the United States. I'm just saying it's not nearly as common as chert. Let's talk about coal, then I'll come back to limestone versus dolostone. Coal is a biochemical rock always, because it's made up of plants that have decayed into some type of a shale. So got to get that part first. You're like, well, shale's detrital. Yep, it is. So the mudstone contains this organic stuff, and the right conditions are present, like swamps, where it gets captured in the rock, and over time it becomes very organically enriched as that material decays into the rock. And so you get what's called coal, and that is a form of fossil fuel material. So the carbon content, and I identified this in your book, actually, if you look into the section for sedimentary, there are 4 different types of coal. So the big question is, do you have lignite, subbituminous, bituminous, or anthracite? And if you read the book, it can tell you. The more it's been basically heated up and pressured, which is a metamorphic process, then the more you're going to have it become condensed and shiny. So the higher metamorphic version of it would be anthracite, and the least would be lignite. Before it ever becomes coal, it's peat. So I'm going to go ahead and lump bituminous and subbituminous together in one group for this lab to make it more simple. So you're basically looking for lignite, the bituminous group, or anthracite. And there is a really good way to tell the difference between the 2 or 3. All right, so let's go back to limestone. So I mentioned biochemical. Really, you could argue that all chemical rocks have an element of biochemical, because most have some form of dead animals there. So I want to hit that one head on, but we kind of call limestone chemical most of the time. It can come in a lot of varieties: chalk, karst. So when we talk about chalk, we have a lot of that in and around the college, because we're on a geologic formation of chalk, limestone. And so it feels like chalk. It looks like chalk. And in fact, that's where chalk is derived. So you'll feel that residue on your finger. Then coquina is made up of shells that get stuck together from along a beach line, and they create a limestone-based rock. So surely they can have sediments that are sand and so forth, but the key is it 50% or more shelly material, and that trumps it as being limestone. If you have oolitic, they're little balls. Some of them can be bigger or smaller depending on the aqueous, meaning water environment. Typically warm waters in the ocean or caverns can produce this, but oolitic has a distinctive kind of little bumpy texture to it. And fossiliferous, well, most all limestone has some fossils that are microscopic, if not predominantly. Fossiliferous is where you can see that. So you may go, well, how's that different than coquina? Most of coquina are shells that don't meet the definition of fossils. Not saying that's always the case, But fossiliferous refers to ancient organisms you can clearly see in the limestone rock. So how's limestone different from dolostone? Chemistry. There is an extra molecule in dolostone of something that you learned about in your lecture that makes it just slightly harder than limestone. Some of the dolostone can be beautifully banded, gorgeous rocks, and others can just be very plain like limestone. But the key is it's a little harder, so you don't have as many places that produce dolostone in the United States, but there's some areas that are very much dolostone. So if you had your choice of limestone or dolostone to make a house out of, if you lived in a side of a cliff that had these, I would choose dolostone, and because it doesn't karst as easy as limestone. It certainly can, but the karsting is more indicative of limestone stuff. So that's a lot to share, but it's necessary because as we go through this, I need to refer back to these things for you. So pick up sample 1, and as I touch it, I want you to get a hand lens on it. And I'm looking at it. I can see some layering. And if you get that on, you'll see that same layering. But the little clasts that make it up are just so incredibly tiny that I can't even begin to see them very well. I can just see the layering. So that would suggest to you it has a very small diameter. If you touch it, it's fairly smooth. You can feel that it's maybe has a little roughness to it, but not much. I mean, it's really fine grained. But the key is that small layering. It almost looks like layers of paper. And that's characteristic of a detrital rock that has the smallest clast size. All right, so pick up sample 2, and I want you to touch it. Remember, you need to be having done all the tests, the hardness, the streak, the magnet, the taste, and then, of course, acid. So feel this one, and you'll likely get a residue on there. I'm going to get my hand lens on this, and I can see some little bits of stuff that looks like other junk, maybe pieces of sand or shale. But what I see is a lot of whitish material. And if I put acid on it, reacts. And there's a reason it does, because it's made of calcite. So just because it reacts does not make it chemical. But remember what I said about the chalky feel? That's what you're seeing here. And that's what you're looking at. So what is it? Let's look at sample 3. Pick it up. This one could actually react to acid if there's some limestone in it and calcite, but when I look at it, I see just all different sizes of stuff. And this came from a bigger rock, meaning a much larger size rock. And it was broken down, so we'd have samples for students to have in these boxes. You're like, well, I can see the grains, but they're not huge. Well, they're big enough to be qualifying as the largest category of detrital. So my question to you is it predominantly rounded or angular? And that should tell you what you've got. I see predominantly rounded. That's what I see. So pick up the next one, and you're going to notice that it probably is fairly, maybe falling apart a bit. So it's not very well cemented. And if I get it under a hand lens, I can begin to see some clast. That's important. So I want you to touch this one in comparison to 1. Notice it has a little bit more grit. That's important. It has more or a larger average grain diameter size than number 1, but it doesn't feel sandy to me. So what rock would that be? Let's pick up number 5. First thing, let's look at it and do all the tests to it. And I can begin to see clast with no problem in this when I get it under some kind of a hand lens or magnification. But I touch it and I feel it to be very gritty and sandy. So remember, shale's not gonna, it's gonna be softer. It's not gonna feel nearly as gritty, like it's pretty soft. Siltstone has a little grit because there's still a little sand in it. And then sandstone feels sandy and gritty. So that's, what are you feeling here? You got to make that determination. All right, let's move on to sample 6. Sample 6. Touch it. Be careful. Some of your edges may be sharp. Get that hand lens on it, and you're going to see very, very fine laminate layers, meaning tiny little thin layers. And I want you to feel it based on number 1, and it even feels softer than number 1, right? So this is super fine grained clast material. And it can't be chemical because I can actually see the layering in it. So what do you think it is? Super tiny clast. And there's your answer. Looking at number 7. When you get into number 7, you don't even need a microscope or a hand lens to see this, but I'm just doing it to model the behavior. This thing is full of fossils. I can see them. It's going to react to acid. I know it's a form of limestone, so which one would it be? All right, let's look at the next one, 8. So when you look at this one, I'm actually going to test it with some acid in front of you right now to see what happens. I've already tested it. There's a slight reaction. And that's because it's not that different from the prior rock. But it is a different chemical sedimentary rock. And if you recall what I said earlier about the difference between limestone and its sister rock, this one is just a little harder because of an extra molecule that it has in its chemical makeup of a very special mineral. So that's what you got here. All right, pull out number 9. I want you to feel it and look at it and think about what it is. You've likely seen this all your life. Very, very common. And in addition, we talked about this being one that's been a reprecipitated version of other chemical sedimentary rocks like limestone, and often used to make arrowheads. So that's a pretty easy build a fit on what that might be. Move to sample 10. All right, feel this one. And I can see grain sizes of the actual clast when I get in here. They're smaller than like what I could see in sample 5. But it's still pretty gritty and sandy. So it's not just a small amount of grit, it's a lot more grit. So it's got to be bigger than siltstone, but smaller than conglomerate. And that should tell you exactly what you're looking at. All right, so get all your stuff cleaned up. Let's go ahead and move into the remainder of the samples once you've done that. Right, welcome back. So as you're doing these, it should be obvious. You can pause them between each and every sample to get your stuff squared away. As we're going through the individual samples in these, so you can constantly stop the video and look. So looking at this rock right away, I've given you all kinds of clues at the bottom. So I'm just going to briefly walk you through 11 through 25 and say, I want you to look at this rock. I'm going to tell you that it will react to acid. That tells you it's got calcite in it. It's made predominantly of calcite. Pretty much that is what it is made of. And I see stuff like this in it without a microscope. So what is it? And it's a specific type of that particular rock. Matter of fact, if you were to start looking all through this rock, I can see some more fossils here, here. There used to be a fossil here. So there's looks like there's something right there. There's definitely something right there. Those are all fossils that you can see without the aid of a microscope. Let's move into sample 12. All right, looking at this, you got to ask yourself, are those sediments? Or are they something else? So what I discussed is, I discussed the difference between various different clastic sizes, and then we talked about various different types of chemical sedimentary rocks. So let me start this conversation off by saying this will most assuredly react to acid. And the shells that you see here are so thickly put together and loosely cemented, I might add, making it a very unique type of rock. What is the name of that? So in your assessment for lab, there are very specific choices for these. All right, let's look at this one. So I've already given you the clue that it's clastic, but you need to look at the morphology. When we're looking at big clasts like this, because the rock that you're seeing here is about the size of an orange, a large one. And so these clasts are very large. And with that in mind, is the dominance rounded or are they angular? That should tell you what you have for sample 13. So as you move through the process to sample 14, if you were to touch this, I would tell you it would be very similar to your sample number 4. And when you look at it, touch it, if you were touching it, would have somewhat of a grit feel, but not a sandpaper feel. That should tell you what it is. And look down here, you'll see your clues that clearly tell you what it is. All right, looking at sample 15, pretty, right? That just comes from the oxides, hematite and oxides that are in there as it becomes an oxidation chemical weathering process. And it brings out the iron in the rocks. So the clasts here are between 0.0625 up to 2 millimeters in diameter. It definitely has a sandy feel to it. So what rock do we have? Moving into sample 16, this will react to acid. Notice holes, and understand the holes are made by slightly acidic groundwater over time that eats through it. So much like you put the acid on a rock that has calcite, it can eat away that calcite. That's what's happened here when you get slightly acidic groundwater. Sample 17. What does that look like to you? I also might point out there looks like there could be some limestone here that hasn't been fully reprecipitated, but this part has. That's a very big clue, okay? So what do you think this is? Moving on to sample 18. So this has a lot of ancient plant material, and this biological material has not been compressed or heated much. So it has a very, very low percent of carbon, and specifically it's referred to as a brown version of this. If you look in your book, you'll know exactly what that is and the carbon concentration. All right, looking at sample 19, there should be no question that you're looking at a detrital sedimentary rock because the clasts are everywhere. I mean, you can see them. You have pebbles of all different sizes, and they're cemented together. The key is, are they rounded, more than 50% rounded, or are they more than 50% angular? And that should be your answer. All right, let's look at number 20. All right, so you get number 20. Do you see that layering right away? So we're dealing with small, tiny clasts, literally less than 0.002 millimeters in size, that have buried over time and made a rock that is about the thickness of a book. So this rock layer, wherever you find it, this is right off of MCC campus that I got this, it took a while to deposit all of those sediments, where if I had one that was the same size of maybe of a conglomerate, it could happen in one storm that could deposit that same thickness of material. All right, 21, pretty, huh? All right, so going back to the other one that had a lot of, we were talking about carbon, this has the highest carbon concentration. So it came from biologic material like plants, but it's been undergone a lot of heat and pressure, and that's why it's so shiny and it's been condensed. So what is this? So sample 22 on, we're interested in the type of sedimentary structure it is. Yes, we care about the rock type that it is, but it's the sedimentary structure we're looking for. So the clast are 0.0625 to 2 millimeters, making it a sandstone. But what I care about are the angle of these layers. Some are at this way, some are at this way, creating a very distinctive type of sedimentary structure that we extensively talked about in lecture, and it's in your book. 23, you're like, oh, I know what that is. Well, super, bravo. These are ancient versions of probably what you can even see around your yard when your yard dries up, and if it has clay in it, it'll do this, but it can happen in just about any type of environment, meaning of clastic rock, can be shale, siltstone, sandstone. And this is a very, very low diameter range siltstone is what you've got here. And it's dried up, and these things right here are the structure that we're looking at, where the arrow is pointing to, where the mud is kind of separated and dried. All right, sample 24. So you've got a conglomerate here. And what we see are big sediments, medium-sized sediments, and small sediments. And then we see another repeat of that, one group at a time. So there's a series here, there's a series here, there's a series here. What do we call those sedimentary structures? Last one. You have evidence that water has moved over these sediments, and you're looking at a siltstone here, and it's left that water emphasis into the sediment, and it's been lithified or hardened. So this is a very common type of sedimentary structure. You know what this is. So what do we call these things? All right, so this is my clue for sedimentary. This is a bird bath of mine. I love this colorful stuff. And so if you have questions about the sedimentary lab, I'm going to ask you about this and some of the other things you see in this picture. This should not have been a very difficult lab for you. Actually, it probably was a lot easier than the other two that you've had thus far. And it's because you're getting better. It's not just because the content's easier, because it's not. It's the same level of difficulty. The good news is you're getting better with each and every one of these. And that's what happens as you practice. So oftentimes students are like, well, I'm never going to get good at this. Only way you do is by picking up stuff and looking at it, touching it and feeling it and studying it. So that's the key. So our next lab that we'll be doing like this is over metamorphic rocks, and it is going to be lab 8. So we'll be doing that next time, and you've got to be sure that you're prepared before you do these labs. Thanks for your time today. I'm super proud of you, and keep up the fantastic work. Bye.